Hello, chemistry students. This is Sean McMahon, and this is our third lecture for Chapter 3, Topics in Energy and Matter. This might be slightly different than the PowerPoint I gave you, just because I always do a few introductory slides. After like one or two slides, it should match perfectly with the PowerPoint that I provided you for my lecture. But last time, we were discussing the types of energy, and the focus was based on kinetic energy, which has to do with motion, potential energy, which is based on position between two objects where there's an attractive force. So like gravity pulling down on an object will bring it to the ground, or in an atom in the nucleus, there's a positive charge and electrons outside of the nucleus are attracted to that charge. So potential energy is based on position. And the total energy of a system is a combination of both its kinetic energy and potential energy, and its ability to either take in energy from other sources or give energy to other sources. When we're thinking in terms of chemistry, I want our focus to be, okay, we have kinetic energy in what form? Heat. So the transfer of heat is due to the movement of particles. That is kinetic energy, so heat transfer. Potential energy, which is based on position, I want you to think of that in the form of chemical energy that's stored in the bonds based on the position of electrons of the nucleus. So when we talk about calories, that is a measure of energy that will be either released or required to burn, let's say, that consumption of food, to burn off that amount of food consumed. And again, that would be potential energy, stored energy. And lastly, the units that we'll be using again is 1 calorie, which is a unit of energy, is equal to 4.184 joules. And the dietic calorie, which is a capital C, is 1,000 calories or 1 kilocalorie. And last lecture, we did some of those calculations converting in between. So for today's lecture, we're going to continue our discussion with heat transfer and units of energy. But what we want to focus on is something called specific heat. Some books refer to it as a specific heat capacity. But basically, specific heat is the amount of heat that raises the temperature of 1 gram of a substance by 1 degree Celsius. And this is different for all substances. The way you can think of it is, how good is a substance at absorbing energy and maintaining temperature? Okay, so the higher the specific heat, the better it is at maintaining temperature. So typically how specific heat or specific heat capacity is written as a formula is specific heat is C. Now this throws people off, but the heat, okay, so we were doing heat kind of calculations before in terms of joules and calories, is Q. And I know that's a little tricky, but just that is the variable. Mass makes sense because it's M, and change in temperature is a delta T, T for temperature, okay? Whenever we say change, what the delta symbolizes is a change, and it's usually from a final temperature, and it's minus the initial temperature. So that would show how much something changed. So a change in temperature of 1 degree Celsius, that would be something like going from 25 degrees Celsius to 26 degrees Celsius. So 26, because that's my final temperature, minus 25 would be a temperature change, a delta T of 1 degree Celsius. So that's what specific heat is doing. Like, right? How much heat do I need to put in for 1 gram of the substance to go up 1 degree Celsius? So the international system of units, we use joules per gram degree Celsius because joule is a unit for heat, grams is a unit for mass, and delta T, we use degrees Celsius because that's what we use. Now in the metric system, instead of joules, we're using calories. That's why we talked about before the conversion factor of there is 1 calorie per 4.184 joules, so that we can convert the unit of heat back and forth. One of the things that I wanted to show you is the different specific heat capacities or specific heats of substances. So if we look at metals, in comparison, they have a very low specific heat to water. Water has an extremely high specific heat. Now, why is that? It has different modes of absorbing energy and kind of compensating for it. So some forms is, if you think of the water molecule, right? You can have what are called stretches or vibrational energy, where it kind of stretches where the bonds are getting closer. Because remember, these are like springs. So they can, kind of go like this. They can go in and out together, those bonds, or they can flex within a plane, right? So you have these types of stretches. The other thing is you have what's called rotational energy. So the water molecule can rotate. That's a way of absorbing energy. Or translational energy, where it's going from X to, from one position to another. So like a delta X displacement. You don't need to know all the modes of absorbing this energy to maintain heat. All you need to know is water has a really high specific heat. That's why, people want to live by the coast in San Diego, because the ocean helps maintain the temperature and keeps it a consistent, roughly 72 degrees Fahrenheit year-round. That's because water has a high specific heat. Another way of you thinking about it is, if you're cooking water in, let's say, a copper or iron pot, what gets hot first? The metals, right? So the pot gets hotter than the water first, and that is just vibrating. And then that vibrational energy is transferred to the water molecules and starts to help it to move faster and faster and have more kinetic energy, which is thermal energy. But the water can retain its temperature for a lot longer because it has such a high specific heat. So I always tell students, I know we just kind of derived earlier, the specific heat formula, but I like to use Q equals mCAT. Now, the reason why I like using Q equals mCAT is because people have heard, especially if you're a STEM major, of the mCAT, which is the entrance exam for medical school. So it's just a little acronym to help me remember. Again, Q stands for heat, which could be joules or calories. M is mass, which is grams. The specific heat capacity was like joules per gram degree Celsius. The only one you should know is water. It's 4.184, right? So if we look at that earlier slide, water is 4.184 joules per gram degree Celsius. What that means is, if I have 1 gram of water and I want to go from 25 to 26 degrees Celsius, I need to put 4.184 joules, or also 1 calorie per gram degree Celsius. So water is a good reference point, because 1 calorie, we use that reference of 1, just like water's density is 1 gram per mil, 1 calorie is required to raise 1 gram per degree Celsius. And then obviously the delta T is the degree Celsius. So the degree Celsius cancels, the grams cancels, and that's how you're left with joules or calories. Okay, just remember Q equals mCAT. So now, why do I bring that up? What is the specific heat? Okay, so now they're asking, what is the specific heat? And I can use a formula here instead of conversion factors of C, specific heat of C, of a metal if 24.8 grams, that's my mass, absorbs 65.7 calories, that's my energy, my heat, but it's goofy because it's Q. And the temperature rises from 20.2 degrees Celsius to 24.5 degrees Celsius. So I have a metal, I have 24.8 grams of it. I put into it, because it's absorbing 65.7 calories of energy. The temperature rises from an initial temperature of 20.2 degrees Celsius to 24.5. That's the final temperature. How do I solve for the specific heat? The ability of this metal to absorb energy. Q equals mCAT, right? So what I'm going to do is I'm going to write down what I know. I know there's 24.8 grams. That's my mass. It absorbs 65.7 calories of energy. That's heat, that's Q, because heat is a form of energy. There's a change in temperature. Remember, I'm always going final minus initial, and I get 4.3 degrees Celsius. So now, right, I need to solve for C in this equation. So what do I do for both sides? I divide both sides by the mass delta T to cancel out, and that would give me my C. So my specific heat is Q divided by the mass delta T. The Q, the heat, is in calories. I have grams here, and I have delta C, so now I can plug that in. So to solve, the 65.7 calories of heat divided by the 24.8 grams of the metal, that change in temperature, 4.3 degrees Celsius, would have a specific heat of 0.62 calories per gram degree Celsius. And this makes logical sense because remember, water has a really high specific heat, and water specific heat, if it's in units of calories, is 1 calorie per gram degree Celsius. So this is 40% higher. Water has a greater specific heat than this metal, this unknown metal. So that's an example of calculating specific heat. Now, in your sample exercises, you have a problem asking for you to solve for the specific heat of silver. And again, I know you could type on Google and figure out the specific heat of silver, but in this class, you'll need to show your work to get full credit. We're not using Google or Chegg or any websites like that. We have to actually be able to solve for it. So you can pause this video and try to solve it just the way we did, or we can go straight into solving it. So how are we going to do that? Q equals mCAT. What do I know? Find the specific heat of silver. So I'm looking for the C. If I have 38.5 calories, so that's my heat, I have 25 grams of it, and I'm going from 31.5 degrees Celsius to 58.7. So that's my initial temperature, and that's my final. Now, what's tricky is my heat's given in calories, but they want the specific heat in joules. What I can do is I can solve for the specific heat, leaving calories, and then eventually change it to joules using that conversion factor that we learned last lecture and applied in our sample exercise problems. So 25 grams, 38.5 calories, just like before. So I have my mass and I have my Q. I solve my delta T, the final temperature minus initial, so 27.2 degrees Celsius. I rearrange Q equals mCAT to solve for C. For right now, I'm going to leave it in terms of calories. That's okay. And then I solve. So I plug in my values. There's 38.5 calories that are absorbed by the silver. There's 25 grams of the silver, and there's 27.2 degrees Celsius of a change. I get this value, and it actually goes on and on. I'm underlining in red that there should be 3 sig figs because I have 3 sig figs in my numbers here. So when I need to get it to joules per gram degree Celsius, I take the answer that was in calories per gram degree Celsius, but I need to get rid of calories. So what do? I put calories on the bottom, and I use this conversion factor that 1 calorie is 4.184 joules. The unit of calories cancel, and I'm left with joules per gram degree Celsius for my unit. And when I do that, when I take this number and I divide it by 4.184, I get 0.237 joules per gram degree Celsius, which is about what we were seeing in that prior slide, okay? So it's a much smaller specific heat than water, which would be 4.184 joules per gram degree Celsius. So these heat calculations, what we're realizing is we have this material and it has a certain capability of absorbing heat or releasing heat. And that's ability is really its specific heat. And the higher it is, the better it is at maintaining temperature. We can see that the silver has a very low specific heat. So we had a pretty drastic change in temperature for a small amount of calories. That's basically what this is doing. So we can take that Q equals mCAT, and it actually shows us whether heat is lost or gained. So typically when you lose heat, that's negative. Like if I lose something, if you gain heat, that's positive. So if heat is Q, when Q is negative, you're losing. If Q is positive, you're gaining. Okay, so in the previous problems, they're saying find the specific heat of silver that's required for silver to go from 31 to, we can see that there's an increase in temperature, so that was gaining the heat or absorbing the heat, right? So that's why your Q here is positive, because it's a gain. So again, M stands for mass of the substance in grams. The temperature change is delta T, or this should be delta C, right? Or yeah, should be your C for Celsius. The specific heat of the substance is either calories per gram degree Celsius or joules. So we can do another problem. So another problem is, all right, let's try this using Q equals mCAT, just like we did before. And in this case, we might not need to rearrange it, okay? So a hot water bottle contains 750 grams, so that would be my mass, at 65 degrees Celsius. So that's initially what the temperature is. So I'll just say this is TI. If the water cools to body temperature, which is 37 degrees Celsius, that would be my final temperature. How many calories of heat could be transferred to muscles? So how many calories can be transferred to the muscle? And what I need to remember is for calories, I'm looking for Q. So how do I do this? Well, I want Q because I want calories, a form of heat. How many calories of heat? And then I have my mass, which is 750 grams. That's Q equals, so I'm doing Q equals mCAT. My specific heat in units of calories, because they want calories, for water is 1 calorie per gram degree Celsius. And now my temperature is 37 degrees Celsius minus 65 degrees Celsius. So what I end up getting, Q equals 750 grams. I still have the 1 calorie, because that's specific heat of water per gram degree Celsius. Actually, the grams cancel. And I'm going to get a negative, what is that value? 28 degrees Celsius here. And the reason why it's negative is the temperature dropped, right? So the hot water bottle transferred its heat to a sore muscle. So the hot water bottle is losing heat. And how do we observe that? We see that there's a drop in temperature. Went from 65 degrees Celsius to 37. So the water bottle is losing heat. And we see that because now we have a negative temperature change. It's dropping in temperature. When I calculate this out, I get Q equals negative 21,000 calories. Now, it wanted to know how many calories. Just to put things in perspective, this is the same, and there's only 2 sig figs, 1, 2. This is the same as me saying negative 21 kilocalories. How come? Remember, in one kilocalorie, if I use the metric system, there's 1,000 calories. So I'm just crossing out those 3 zeros and I get that many kilocalories. The reason why I turn it to kilocalories, because remember, that's a dietic calorie, big C, right? So that's how many dietic calories 750 grams of hot water at 65 degrees would lose to the body, right? If it dropped down to body temperature of 37 degrees Celsius. So it would lose 21 dietic calories. And the reason why we know it's a loss of heat is because that negative sign, right? All the other ones where the metals were absorbing heat, that was a positive sign. So is the sign important? It is. The sign is important because it tells you the direction. Am I losing heat or am I gaining heat? So a lot of times in chemistry, especially with these types of heat calculations, sometimes also referred to as thermochemistry, you want to have a reference point, okay? So typically there's something referred to as a system. That's what you're looking at. So in those earlier problems, we were talking about the specific heat of the metal. The metal was a system, okay? And it absorbed energy from the surroundings. In that last problem, the hot water bottle was the system, okay? It lost energy, okay? That's why it was negative. When we talk about chemistry, the system is the reaction, okay? So here's the system, this balloon, I'm studying it, right? The surroundings is everything outside of the system, okay? So with the hot water bottle, it lost heat. Why? Because you put it on the sore muscle, and when it was warmer than the muscle, it gave the heat to the muscle, and the muscle warmed up, and the hot water bottle cooled down. That's why it was negative. And it lost heat. That's why it's negative. But the muscle is in the opposite direction, so it's gaining that heat. So the muscle would have actually had a positive heat change. Typically, when we're doing studies for heat exchanges, we use what are called calorimeters. That's why we use that unit of calorie as a reference point and water being 1 calorie per gram degree Celsius. But in this case, if this balloon animal is the system that I'm studying, then the fire would be the surroundings because it's outside of the system. Now we know that if this fire is losing energy, right? Because really, whenever you burn something, that loses energy. And someone might say, but it's giving off heat. That's right. It's giving off heat because it's losing the heat. And this yourself, let's say, you know, the fire, you burn wood, so it releases heat. If you're the system, you're absorbing that heat so that you can stay warm. So it's equal in magnitude, the amount of heat. It's just opposite in direction, and that's why we use a sign. And typically you go from high potential energy to lower potential energy, okay? So basically for heat transfer, you know, you go from hot to cold because cold has less energy. So why do I bring this up? Because reactions, remember we talked about reactions, right? When we study chemistry, matter, there's changes in energy. So a lot of times in reactions, you can release energy or you can absorb energy. An exothermic, so I want you to use your prefixes and your roots. Exo, exoskeleton, outside. Exit, leave. Exothermic means you lose heat. And when you lose heat, Q is negative. Anytime you lose something, it's negative, right? If you lost money, that'd be negative. An endothermic reaction, endo, right? Enter, right? If you're going to enter, entering means you're gaining heat or absorbing. And that would be Q equals your heat is positive. So combustion, the burning of wood, is exothermic. It loses the heat. But the surroundings, my hands, is endothermic because now it's absorbing the heat. So that value of Q is the same. It's equal in magnitude. You can think of it as almost an absolute. It's equal in magnitude, but it's just opposite in direction, and that's what the sign tells me. So exothermic releases energy to the surroundings. So we can't really measure the temperature of the bonds in a reaction break-in. They're too small. But what we could do is we could put that system, that reaction, into surroundings, like let's say water, okay? So the system, the reaction itself could lose that heat. So the system would be a negative. But the surroundings, if the system's losing heat, would gain the heat. So the surroundings would get a positive heat. And how would you measure that? You would measure the temperature and the change in temperature. So the change in temperature would rise because we're measuring the water, which is surroundings. That's why this is hard for students, is because in chemistry, you can't really measure the reaction. You can't measure the system, so you have to measure the surroundings. So it's kind of backwards. It's hard. But with exothermic reactions, the way they work is they go from higher potential energy to lower potential energy. That's why I have this graph. You can think of this as my potential energy. Where are we getting the potential energy? The stored energy based on position. The bonds. Remember I said electrons and their distance to the nuclei? Well, in a reaction, I could have reactants and I break their bonds, and then I form new bonds where now the atoms are closer to each other rather than further apart. So their bonds, instead of being farther apart and having more potential energy, their bonds are now closer. So now they have less potential energy. So they go from a higher potential energy to a lower. So what do you do with this difference in energy? Now remember, we can't create or destroy energy. We can only do what? Transform it. So if I'm going from a higher potential energy to a lower potential energy, I can't just get rid of it. So what do? I convert potential energy to movement kinetic energy. And in a chemical reaction, that lowering of potential energy is releasing it in the form of heat. So what's an example? I burn butane in that lighter or wood or whatever in the presence of oxygen, and I produce simpler molecules like CO2 in water. So I go from higher potential energy, more complex subs, to simpler. So when I do that, there's a difference in the potential energy. So I can't lose the heat. I can only transfer it, or I can't lose that energy. I can only change it. And then I end up producing heat. And I feel as part of the surroundings, the heat being released. So the system is losing energy, but the surroundings is gaining the energy. So you can identify an exothermic reaction because if it's, let's say, in a test tube or a beaker, if you touch the beaker, the glass, the surroundings of the reaction, it'll get hot because the actual reaction is losing that heat. So it's kind of backwards. I know it's tricky. Well, what about endothermic? It's the opposite. An endothermic reaction, to get the reaction to go from a lower potential energy to a higher, you have to put energy into the system. Where is that energy going to come from? It's going to come from the surroundings. So the reaction is going to pull energy into the surrounding, into its system from the surroundings so that it could occur. So what would that look like? So the system, the reaction, if it's endothermic, it needs to gain heat. Where is it getting the heat from? The water molecules. So now the water might move slower because it's got to transfer that energy into that system. And then if the water is losing energy, that means the surrounding water, right, it's losing, would be negative. So how do we measure the surroundings in an endothermic process? It's kind of weird. Like, how do we show that the reaction's absorbing energy? Well, it has to get the energy from somewhere. Where? The surroundings. So I measure the temperature of the water and I see that there's a drop in temperature. And that's why with that last sample exercise 8, right, the change in temperature was negative and the Q was negative because it was losing heat to the leg, right, or the sore muscle. But how does that look? So if the reaction in here needs energy to go to a higher state, I need to put energy in to get it to a higher potential energy. How do I do that? I take it from the surroundings. This is what's done for diets, how to determine the number of calories in a food source. It's called calorimetry. So you basically measure the heat transfer. Well, how do you do that? You have a food sample that burns in a chamber, right? Surrounding that chamber, the surroundings, right, is water. And then this is the system. When it releases heat into the water, I can record the rise in temperature and see how much energy the water absorbed, right? So that's basically that. So typically it's measuring exothermic reactions. What is exothermic? So the food, an exothermic reaction is when it loses energy. When I burn food, it gives off heat, loses heat, exothermic. What does that mean? The calorimeter is water, the surroundings, gains it and goes up. I can measure the temperature change, and the heat transfer is equal in magnitude, just opposite in direction, just a sign difference. In lab, you use a coffee cup calorimeter. You literally get 2 styrofoam cups with a coffee lid, you put a thermometer in there, you add your reactants in there, you stir it, and then you record the temperature change, and then you use Q equals mCAT to calculate the energy transfer, and then the Q gives it in either calories or joules, just like those problems we solved. So on food labels, calorimeters, calories, you know, we see the big cal. And again, the big cal is 1,000 little cals. The big cal is basically a kilocal. Okay. And for the most part, we know that 1 calorie, 1 little cal is 4.184 joules. So if I have 1,000 calories, because this is big cal, I move that over 1, 2, 3. That's 4,184 joules for a calorie, a dietic calorie, a kilocal. Okay. So why do I say that? Well, you might have a couple of problems that have you calculate how much energy per gram of food. So here's an example, right? If I have 4 grams of fat that I burn in a calorimeter, it's going to release heat, and I can measure the water using Q equals mCAT, and I can see that the water absorbed 164 kilojoules. Can I calculate the energy of fat in terms of how many kilojoules are released per gram of fat that I burn? Yeah. 164 kilojoules of heat are released per 4 grams of fat that are burned. So I'm going to get 41 kilojoules per gram of fat. Now, this is, you know, for this particular sample. And if we use, you know, generic, because not all fat gives you the same amount of energy. There's, you know, saturated fat versus monounsaturated and polyunsaturated. So different fats actually give you different amounts of heat per gram. But if you were to take a ballpark, an average, typically a gram of fat is going to give you about 38 kilojoules. A gram of carbohydrate on average is about 17 kilojoules per gram, and it's the same as a protein. But I think most people have heard of the kilocal per gram, because the kilocal, remember, is a dietic calorie per gram. So it's basically 4 dietic calories per gram of carbohydrate and protein and 9 for fat. So what you see is to burn 1 gram of fat compared to a gram of carb or protein is more than double, because fat has far more energy stored in the bonds. It has more potential energy. So because it has more potential energy, it will release more energy in the form of heat, right? When it transfers that. And you can look at packages. I mean, they show you, you know, how many calories, how many kilojoules, and remember, this is a big C, dietic calorie, how many kilojoules, calories from fat, they tell you how many grams of fat, they'll tell you how many grams of carbohydrates, tell you how many grams of proteins. So that's really useful. Now, this is just to give you an idea. You can take a banana. It's got 26 grams of carbs and pretty much 1 gram of protein. It comes out to roughly 110 dietic calories. Okay. So if I got, chicken with no skin, 3 ounces of it, it's about 110 calories. Very high in protein. I mean, chicken's really high in protein. It's a lean meat. There's not a lot of fat, right? A lot of people love eggs, right? Why? Well, what's so great about an egg? Well, it's got it's considered the perfect protein because it has all 20 amino acids required for protein synthesis. But it's got 6 grams of protein and it's got a very low calorie content, So we should be able, using, these amounts, we should be able to calculate, if I have a sample of food and I know the breakdown of carbohydrates, fats, and proteins, like in the back of a label, how many grams, I should be able to calculate how many total calories. So in exercise 11, we do just that. A cup of whole milk. So 1 cup is 8 fluid ounces. So, a can of soda is 12. All right. So it's only 2/3 of a 12 fluid ounce can is a cup, and it has 12 grams of carbohydrates. It has 9 grams of fat and 9 grams of protein. How many kilocalories or dietic calories are there? Okay. So 12 grams of carbs. Well, I'm going to use a conversion factor. Carbohydrates per 1 gram of carb, there's 4 kilocalories. And I'll do the same for fat, but except per 1 gram of fat, it's higher in calorie content, 9 kilocalories. And then over here, per 4 grams of protein, per 1 gram of protein, 4 kilocalories. So when I add this up, 12 times 4, 48 kilocalories. 9 times 9, 81 kilocalories. 9 times 4, 36 kilocalories. When I add those all up, I get 165 kilocalories, but it says to the nearest tens kilocal, it'd be 170 kilocal, which we know that basically means 170 dietic big C calories. So a cup of milk is about 170 calories, whole milk, that is, right? And, this is 4%, so it's a little bit different here, but yeah, pretty good. So what are energy requirements, right? Because our body requires energy to do things, okay? Even when we're at rest, we're doing stuff. We're making proteins. There's neurological synapses. We're rebuilding muscle. We're keeping our body warm. So even at rest, there's energy requirement. Well, this is for an energy expenditure for a 154-pound adult, right? So if they're sleeping, they need 250 kilojoules per hour. I like kilocal because then it's dietic calorie. 60 calories per hour just to sleep, right? If you're just sitting down, you're not even exercising, you need 100 calories per hour, right? So if you were sitting for 24 hours, which you're not going to do, but that would be 2,400 calories, 2,400 calories, right? A good chunk of 8 hours you're sleeping, walking, 200 calories per hour, right? So a candy bar that's 250 calories, you got to walk for an hour or more, really, an hour and 15 minutes to burn off that Snickers. I guess you could run, then you would burn it in and swim, burn it in a half hour of swimming, but swimming's hard. To swim straight for a half hour, that's not easy. And of course, this is going to be different based on your age, your gender, your size. There's a lot of factors, and these are averages for a 154-pound person like me. I'm bigger than that, so I need to consume way more food than the average, what they say, 2,000 calories per day. I mean, I would burn that just based on my weight, just sleeping all day. So food intake, this is kind of obvious, and this is something, it's just common sense. If intake exceeds the energy use, you're going to gain weight, right? So how do you lose weight? You either have to increase the amount of energy, so by exercise, or what's actually easier than exercising, right? Because like I said, to swim a half hour straight to burn off a Snickers, what's easier is instead of, working more is eat less, right? So it's basically input, output. However much you put in, if you want to maintain weight, you have to put out that amount. Otherwise, you won't maintain your weight. If you're putting in more than you're burning and require to function, then you're going to add weight. So if food intake is less than what you use, you're going to lose weight. So this is kind of the last exercise. This kind of gives you an idea of, all right, I have the late night munchies. I was studying, I don't do this, but I'm not saying I didn't do this in college when I was younger, because I didn't think about stuff. I had a high metabolism, but for some reason you want to eat 5 bags of Doritos, right? And that walking burns 200 dietic calories per hour. How long would it take for me to burn the 5 bags of Doritos that I ate in like 10 minutes while I was studying? Because I was burning calories because I was thinking, but I want to equate it to walking. So if one of those bags is 150 calories, so we'll say, right, 5 bags, because that's what I start with, right? And I know that in one bag, there's 150 calories. I want to know how many hours that's going to take to walk if I burn. So I'm getting rid of bags to get rid of calories. There's 200 calories per hour of walking. How many hours? Well, that comes out to 3.75 hours. So for me eating that 10-minute binge of Doritos, 5 bags of it, now I got to go walk. And if I was to use sig figs, there's 1 sig fig here. Actually, that's an exact number because 5 bags. So we would use this, and that's 1 sig fig. So that would be, if I use 1 sig fig right there, 4 hours of walking to burn those 5 bags. Okay. Now, a lot of people get confused because they see the 5, they see the 200. They're like, why did you start with the 5? I was looking to see how many hours. So I ended with a single unit. I don't have a ratio. So if I remember from the first chapter 2 lectures, if I don't end with the ratio, I shouldn't start with the ratio. This is a ratio, calorie per hour. I use it to convert a unit, but this is not. So because I don't end with the ratio, I don't want to start, and I started with the 5 bags. So we are actually done with chapter 3, which is a study of matter and energy. And these last calculations, we talked about the ability for substance to absorb energy and maintain temperature based on their specific heat capacity. The higher the specific heat capacity, the better they are at maintaining temperature. And water has a really high specific heat. That's why people like living by the coast, because it maintains the temperature. That's why, in a really dry desert at night, it can get really cold because there's not a lot of, material in the air to absorb that temperature or that heat and maintain that temperature. Instead, it gets really cold at night, but then in the daytime, it gets really hot. because there's nothing to maintain that temperature, okay? So we learned about specific heat, and then we talked a little bit today about the calories. The earlier lectures were matter and the different types of energy. So we finished off matter, the different types of energy, and caloric calculations for diet, and specific heat calculations for substances that we see in nature. So thanks so much for watching, and we are done with chapter 3, and the next lecture will be the first lecture for chapter 4. Thanks for watching. Let me know if you have any questions.